Last of the Chapter 4 exam review. Please remember that usually in the 6 free response questions, there's usually at least one question about experiments and observational studies, particularly how to design an experiment or some part of it. So first of all, make sure you know the difference between an observational study and an experiment. Remember that in observational study, the researchers simply observe individuals and measure the variables of interest, but the researchers do not attempt to influence the response. In other words, in an observational study, you don't apply the treatments in an effort to make a difference. An example of an observational study, if you say you want to do a study to show that helmets save lives, you would assign half of your volunteers to wear a helmet on a motorcycle and the other half to wear no helmet. You would not be able to ethically get away with that. You would not want to make half of them wear a helmet and make the other half not wear a helmet. So that would be a better observational study where you just dig through records, hospital records presumably, to compare the death rates of motorcycle drivers that wear helmets versus no helmets. So the researchers wouldn't apply those treatments. They would simply observe what records already say about the difference between wearing a helmet and not a helmet. Smoking causes cancer. Would you want to assign half of the volunteers to smoke and the other half to not smoke? No, you wouldn't force that treatment on them. You would simply look up records of smokers and non-smokers to see what the difference is in the occurrence of cancers. So those would be good observational studies. An experiment, the researchers observe individuals and measures the variable of interest, but they do attempt to influence the response by imposing different treatments. So you impose treatments in an experiment. So like for instance, you want to do a study where you think classical music reduces stress. Could you get volunteers and assign them to 3 groups? That wouldn't be unethical, right? You people are going to listen to classical music for the next month. You're going to listen to rock music, and these people are going to listen to no music for the next month. And after a month, we're going to measure the difference in your stress levels and compare the 3 groups. That would be an experiment because we could impose those 3 treatments. Examples. A human resources director of a large company is interested in how often employees use their computers during breaks. She watches a selected group of employees at their desks during break times. This is an observational study, not an experiment, because this director didn't randomly assign some people to use their computers this much and others to not use their computers. She simply observed. So that's an observational study. Now, moving into experimental design, lots and lots of terminology. So you may want to press pause on this and do some writing. Make sure that you can answer questions about what explanatory variables are. Explanatory variables are the variable that may be making the changes occur. The response variable is the variable that you're going to measure at the end of the experiment to actually be able to compare. Experimental units and subjects. Subjects are the humans that are taking part in an experiment, and units are dogs or plants, etc., that are part of an experiment. Levels. The different values of the explanatory variable. So like, for instance, the explanatory variable of an experiment could be fertilizer type. And then the levels could be Miracle Grow and some generic. So the explanatory variable is the vague description fertilizer type, and the different levels are, well, what are the fertilizers you're using? Treatments. Well, sometimes the levels are the treatments, but sometimes there's more than one level and you combine them to make different treatments. We'll describe that later. Control group or placebo group. A control group is a group that is used to provide a baseline for comparing the effects of some other treatment. The control group is usually the group that gets no treatment. In a medical study, the control group is called the placebo group. A placebo is a fake medicine. It could be a pill or a capsule that looks just like the real thing, but it doesn't have any of the active ingredients in it. Placebo effect. Placebo effect is sometimes subjects in an experiment respond favorably to the placebo and they experience some kind of psychological cure or relief, if you will. A single blind study. If you can do an experiment in a way where the subjects don't know whether they're getting the real treatment or the placebo or the new treatment or the old treatment, then that would be a single blind study. Or you could do a double blind study where both the subjects and the researchers don't know who got what treatment. So if you were doing a medicine study, drug versus placebo, double blinding would be, well, just make the capsules look identical so the patients, the volunteers, don't know if they're getting the drug or the placebo. And then how can you blind the researchers from knowing who got what treatment? You can have entities outside of the experiment, like, for instance, the pharmacists, who can randomly assign subjects to get the new drug or the placebo, and they do not reveal who got what drug during the course of the experiment. So double blinding, the researchers and the subjects don't know who got what treatment. Confounding. This is what we say happens when some outside variable could have caused the response observed instead of the explanatory variable. Like, for instance, what if you were trying to say that studying causes changes in grades? Well, if you wanted to let study be explanatory variable and grades be the response variable, studying causes an increase in grades, well, there's a lot of things you better control because they could ruin the experiment. Isn't it true that sleep could also have an effect on grades? So we say that sleep could confound the experiment if you don't control sleep. So confounding is when an experiment is ruined by an uncontrolled variable that could have actually caused the change in the response. Yeah, it's fine. It's fine. Okay, looking at some sample problems. These would take too long for me to write as we were doing them, so press pause whenever you need to stop and read what I wrote. This is a problem from the 2019 AP Statistics exam. You could actually press pause and score me. Researchers are investigating the effectiveness of using a fungus to control the spread of an insect that destroys trees. The researchers will create 4 different concentrations of fungus mixtures: 0 mLs, 1.25 mLs, 2.5 mLs, 3.75 mLs per liter. An equal number of insects will be placed into 20 individual containers. The group of insects in each container will be sprayed with one of the 4 mixtures, and the researchers will record the number of insects that are still alive 1 week after spraying. Okay, so part A of this problem said identify the treatment's experimental units and response variable. So I know what treatments are, so I said the treatments are the 0 mLs, 1.25 mLs, 2.5 mLs, and 3.75 mLs of the fungus. The experimental units are the insects that were placed into the 20 containers. The response variable is the number of insects still alive in each container. I realize I shouldn't have said dead because they said record the number of insects that are still alive. So I might have gotten some deductions there. Does the experiment have a control group? Yes, it does. It has the 0 mLs per liter group. So I said that's the control group. We can use that as the baseline to compare the other 3 levels of the fungus that were put in the containers. So we would compare the other 3 treatments to that one. Describe how the treatments can be randomly assigned to the experimental units so that each treatment has the same number of units. Okay, after an equal number of insects are placed into each of 20 containers, number the containers from 1 to 20. Use technology to randomly select 5 numbers between 1 and 20 and assign 0 mLs to those 5 containers, and then repeat that again to pick 5 more containers to get the 1.25 mLs, and so on and so on and so forth. Now, it's after I wrote what I think is a good response to part C that I realized that I'm actually wrong right here. The experimental units are not the insects. The experimental units are actually the 20 containers. Probably would have scored a 2 or a 3 on this one. 1999, number 3. The dentist in a dental clinic would like to determine if there's a difference between the number of new cavities in people who eat an apple a day and in people who eat less than 1 apple a week. They're going to conduct a study with 50 people in each group. 50 clinic patients who report that they routinely eat an apple a day and 50 clinic patients who report that they eat less than 1 apple a week will be identified. The dentist will examine the patients and their records to determine the number of new cavities the patients have had over the past 2 years. They will then compare the number of new cavities. So they already knew how many cavities they already had. Why is this an observational study and not an experiment? The dentist didn't assign for these 50 to eat an apple a day and these 50 to eat less than 1 apple a week. No, they already noted which patients eat an apple a day and which don't. So they did not apply treatments in an attempt to get a different number of cavities in the 2 groups. They just observed over a 2-year period who got more cavities. Explain the concept of confounding in the context of the study. Include an example. Well, drinking sodas can cause cavities, sugary sodas. So soda drinking could confound this experiment. In other words, it could be that the apples were having no effect whatsoever. It was the actual unobserved variable of soda drinking that could confound, that could cause the cavities. If the mean number of new cavities for those who ate an apple a day was statistically significantly smaller than the mean number of new cavities for those who ate less than 1 apple a week, could one conclude that the lower number of cavities can be attributed to eating an apple a day? No, just because there's a correlation between eating an apple a day and getting less cavities does not mean that it's the apples causing the fewer cavities. Hopefully you remember that from our time in Chapter 4. Year 2016, number 3. Alzheimer's disease results in a loss of cognitive ability beyond what is expected with typical aging. A local newspaper published an article with the following headline: Study finds strong association between smoking and Alzheimer's. The article reported that a study tracked the medical histories of over 21,000 men and women for 23 years. The article stated that for those who smoked at least 2 packs of cigarettes a day, the risk of developing Alzheimer's was 2.57 times the risk for those who did not smoke. What are the explanatory and response variables? The explanatory variable is smoking status. Do you smoke or not smoke? Would be the levels if they had asked. The response variable is the number of patients who develop Alzheimer's in each group. Is the study described in the article an observational study or an experiment? It's an observational study. The researchers did not tell these people randomly to smoke and these people to not smoke. No, they already had smokers and non-smokers, and they observed. They did not apply the treatment. Exercise status was mentioned in the article as a possible confounding variable. Explain how exercise status could be a confounding variable. Exercise or lack of it could cause Alzheimer's differences in the groups. So that would need to be controlled. In other words, exercise could be associated with Alzheimer's, not just smoking could be associated with Alzheimer's. So if you don't control the other one, then that could ruin the experiment. 4 key elements of a well-designed experiment. If you're going to write about a well-designed experiment on a free response question, you write about random assignment of people into treatments or dogs into the treatments. You must write about things that need controlled. You have to keep other variables constant among the treatment groups. You only want the treatments to differ by the one thing you want them to differ by. So like if you were doing a tomato plant experiment where you were trying to see if fertilizer A or fertilizer B was better in producing more tomatoes, then if you need those two treatments to be identical in every other way, then you better give them the same light, the same water, the same air, the same containers, the same everything. In other words, you want those two groups to differ in one way, which fertilizer it got. As a matter of fact, you better control how much fertilizer. You better give an identical amount of fertilizer A to its group as you did to fertilizer B. So that's control. There must be replication, and in statistics, replication means having enough experimental subjects or units to be able to distinguish a difference in the effects of the treatments. So, for example, if you only put 5 plants in fertilizer A group and 5 plants in fertilizer B group, that would not be enough to say that there's replication. That's not enough plants to compare. But if you have 50 plants in fertilizer A and 50 plants in fertilizer B, you have replication because there's enough plants to compare, the difference in tomato production to each other. And the 4th element of a well-designed experiment is optional. Sometimes you need to use a block design if a regular design can't control certain things. So like for instance, back up here when I was talking about fertilizer A, fertilizer B, if I had the same species of tomato plant and I divided half of them to get fertilizer A and the other half to get fertilizer B, that's great. We don't need a block design. But what if you went to Walmart and got 50 of one type of tomato plant and 50 of another type of tomato plant? Well, if you were just being random, you would possibly accidentally put a lot of one type in fertilizer A and a lot of the other type in fertilizer B, and next thing you know, it wasn't the fertilizer, it was that this type of tomato plant is more productive than the other one. So if you have 2 different types of tomato plants, then what you would do is you would run the experiment on type A and run the experiment on type B separately. So we'll be talking about that. There are 3 main types of experimental design that I'm hoping you remember. Completely randomized design is when you keep the group whole. So for example, here I've got 100 tomato plants of the same type, and I randomly assign half of them and randomly assign the other half of them to get the 2 different fertilizers, and then at the end I compare tomato production. If you're going to use a diagram to describe a completely random design, you must also write about the way you did this random assignment. Remember, if you're describing a random experimental design, you better talk about how you were randomly placing. It's not enough to put random assignment on these 2 arrows. That is good, but you got to write about how you did this. So, a couple sentences before or after the diagram. Also write about those things that need to be controlled, the water, the air, the light. Then there's the block design. If I had two different types of tomato plants, then a block design would be separate them by type. So I got 50 of type A and 50 of type B. I'm not going to intermingle them. I'm going to randomly assign half of type A and half of type A to fertilizer A and fertilizer B, and then compare. And then separate from that, almost like a separate experiment, I'm going to randomly assign half of the other type of tomato plant to each fertilizer type and compare. And then at the end, I can make a deduction about the two different fertilizers. Then there's the matched pairs design. The matched pairs design is when you have so many blocks that there are only two subjects in each block. Or sometimes there's one subject in each block. So like, for example, if I was doing an acne experiment, drug versus placebo, I could do it this way. I could apply the drug to one side of a human's face and the placebo to the other side of the same human's face, and that way I can actually visibly compare the acne on that one person's face to the same person's face, and then do that for the second person and the third person. Another way of doing a matched pairs design is, for example, suppose that you've got a male 30-year-old and a male 32-year-old who've both volunteered for the experiment. Well, then you can randomly choose which one gets the drug and which one gets the placebo, and then compare just those two to each other. And then, you could do a female 30-year-old with a female 35-year-old, a male 18-year-old with a male 22-year-old. They're close in age. So block designs. The year 2000, number 5, was an experimental design question. Pause and read it, but just to kind of keep going here, this was a cholesterol reducing study. It said, explain how you would carry out a completely randomized experiment. So I said, well, I can take an alphabetized list of the volunteers, number them 1 to whatever, don't say whatever, then use technology to randomly choose numbers until half of them are chosen to be in the new drug treatment. The remaining half will therefore get the current drug treatment. Make sure that you control other variables such as diet and exercise and blah, blah, blah. And then I just always feel compelled to draw a diagram. My volunteers were randomly assigned, half to the new, half to the current, and I'm going to compare cholesterol levels at the end of the experiment. Describe an experimental design that would improve the design in Part A by incorporating blocking. Well, perhaps the genders respond to cholesterol medications differently, I said, so I could block by gender. And I would write a lot of the same stuff as I did above. So I could say randomly assign half of the males to the drug and the other half of the males to the placebo, compare. Randomly assign half of the females to the drug and half of the females and compare. Now, is this the only correct answer to Part B? No. If you were to look at year 2000, number 5, you could see that perhaps some people said block by age, and they described and drew diagrams and stuff like that. So there was more than one answer. They're just seeing if you kind of logically block by something that makes sense. Year 2002, which was one that you've already looked at, this is free response question number 2. I encourage you to look up and read this problem's scoring rubric if you have not already. Many people scored a 3 on this, which is pretty good, but it took a special answer to score a 4. This was about boots and comparing a new method of waterproofing to a current method of waterproofing, and Part A was describe a design. It didn't say describe a completely random or a block design. It said describe a design for this experiment that uses the 100 volunteers. So what if somebody wrote this as their answer to Part A? I took my 100 volunteers and I randomly assigned 50 of them to wear boots that got the new treatment and 50 got the current treatment, and compared the damage at the end of 6 months. And they wrote about random assignment. These people only scored a 2 on this problem. Other people wrote, let's block by gender because, males sometimes can be rougher on their boots than females, they said. And so they said, randomly assign half of the males to get the new and randomly assign half the males to get the current and compare damage at the end, and then do the same for females, and they wrote. These people scored a 3. That's pretty good, a block design, because there were some things that couldn't be controlled by just completely randomness. In other words, you could have gotten way too many males and way too many females, and so it could have ruined the experiment. The people who scored a 4 on this problem described a matched pairs design. They said, what if you took each one person and randomly decided that the left boot got the new treatment and randomly decided that the right boot got the new treatment, and then that person sends back the boots for damage comparison of the left and the right boot, and then do that for every other person. That person scored a 4. Could your design be double blind? Yes. Easily, the people who are wearing the boots don't have to know which boot got which treatment, and also the researchers who are the ones who are going to do the comparison at the end, they don't have to know which boot got which treatment either. You could have an outside entity have treated the boots and sent them on their way. So you definitely could be double blind. Also, you're currently working on the 2007 exam, and what's interesting about the 2007 exam is it had 2 problems that were both about experimental design or observational studies or all of the terminology that are associated with experiments and observational studies. So make sure you look at those as well.